was wrong. Okay? And the referee didn't believe me. I had to have a big fight with the referee. He said no, but I was able to show that that model's defect was due to the way the vertical structure was coming out. Then it was rectified. Now model today that's not as here year-to-year variations were 100% in rainfall over India. So which I pointed out to the economist at that time. So that's a problem. I think he rectified it with some problem with their cumulus scheme. So this is the advantage of this model. It's a diagnostic model, will tell you where in the model you may have difficulty, because other models, for example, had other problems which are related to radiation or this one, but only this model had problem with the vertical structure. Now, so far I talked about seasonal cycle. I talked about how this model is useful to understand the defect in models. Then you might ask, how about the past and the future? We are all concerned about future because climate change is occurring and none of us are really acting fast enough to stop the change. So what will happen? A lot of climate models have been run to look at the future monsoons, and there are differences between models. So how do you understand that? The way to understand is, if you compare, I'll take one example. If you compare the relation between rainfall and water vapor in the future and the present in one of the models, ECAM, MPI, you see a clear displacement. The question is, why is there a displacement? The answer is very easy. For the same water vapor, in the future, we'll get about half the rainfall compared to present. And that's a very frightening story. In the future, temperature will go up, ocean will get warmer, there will be more water vapor, no question about that. Unfortunately, the atmosphere will get more stable. And the amount of mass you can converge will be constrained. And so, for the same amount of water vapor, you will have half the rainfall, and that is the one which we have to worry about a lot if you allow the temperature to go up to 3 degrees or 4 degrees above normal. Now, the other interesting question is about the past. Now, in the last few years, I'm interested in paleoclimate, mainly because wonderful work has been done by Dr. Raju and others, looking at the last 150 years of monsoon rainfall, and they have squeezed out every possible understanding from that. But that is limited because monsoon has variation over century and longer time scale. So if you want to understand the atmosphere ocean coupled system, which has many variations, you have to look at a much longer period. And the only data is paleo. Now, for a long time, paleo data was viewed with suspicion by many people because they are proxy, there are problems, they are not very often very quantitative. But today, the amount of proxies that are coming out is amazing, and we have lots of data from speleotherms all over the world. So today, I believe that the data from proxy evidence is very good, and we have also good climate models. So I'm going to just mention to you a very interesting result from a model run by NCAR for 23,000 years. I'm really amazed how they did it. They ran a model for 20,000 years starting from the last ice age all the way to present, and the data available open, anybody can look at it, and I would welcome many of you to look at it because it's a very rich source of understanding of monsoon. Of course, you have to believe that the model is correct, of course. If you doubt the model, then you shouldn't use it. So this model, we looked at the rainfall in this model with incoming radiation from the sun. And the reason why I looked at it because paleo people always thought that the only driver of the past monsoon is incoming radiation. Yeah, it's very important because before human beings interfered with Earth's climate, the only variability was natural, and which solar was very important. Now, what this shows is, if you go from the LGM to the present, there are two phases, the deglaciation phase and the Holocene. And what this graph shows is that between these two, there's a huge difference in the response to sun's variation. The slope, you can see, is almost double. And nobody has explained this, why the slope should be double. So we use this Needle-held hypothesis to examine this. So just to summarize this, 7% change in the radiation from LGM to the Holocene, that is about 12,000 years, causes 100% change in rainfall. So amplification of 14 times. Now that's amazing amplification. So one has to explain that. And so this is the sun's variation normalized with respect to modern day. Very mild variation. The actual variation is very large. So the large variation you're seeing is not directly driven by sun. Sun is the only variable, but something else is amplifying that dramatically. Okay? And that was not quite highlighted. And what we found was that this quantity, gross moist stability, is the parameter. It varies strongly with water vapor, 1 over water vapor. And we were able to not to look at year-to-year variation, that's large variation, 100-year averages. You take 20,000 years and make 100-year average, you get 230 points, and that's enough to understand this. So that shows, after fitting this curve, a linear fit, the black line is a model simulation, and the red line is a simple model. It's not perfect, but it is able to capture the most important variation of the centennial scale monsoon through simple invocation of the role played by water vapor. Some of the water vapor's role has not been highlighted, mainly because there is no proxy evidence of water vapor. Not easy to get a proxy water vapor. For rainfall, you have proxy. For other things, you have proxy, but not for water vapor. So we believe this is going to improve the understanding of the monsoon. So the point I'm trying to make is that this kind of expression for monsoon is very useful to understand both the past climate and the future climate. Now, I think I'll skip all this because I'm going a little ahead in time. Only other thing I want to point out that traditionally the people in Paleo nowadays explain the change in rainfall through the movement of the IDCZ. The argument is, as the earth warmed, the northern hemisphere became warmed by the southern hemisphere, the IDCZ moves. So this is different from Lansing contrast. This contrast between two hemispheres. Okay? This is a different idea. It can be derived from the Neal-Held hypothesis. You can derive exactly. Okay? But that hypothesis cannot explain why during the phase of Holocene, the rainfall over Bay of Bengal increased, but that of India decreased. Okay? We know that in the last 10,000 years, rainfall has decreased over India, and our model reproduces that. But this part nobody was able to explain, and we are able to explain it because we show that the wind speed of Bay of Bengal changes due to the change in rainfall over India, and that increases rainfall. So we are able to show the role of surface fluxes over ocean. Over land is not important, over ocean is important. So this is again a new result which this new paradigm brings out. And this one, this rainfall has decreased over Bay of Bengal but increased over the rest of the region. Now, so there are two hypotheses here. One is called global energetics, which invokes contrast in the two hemispheres, north and south, not land sea, between two hemispheres, and that's quite popular now. A lot of people have invoked it. But the model I'm talking about highlight local physics, not the global energetics. So these two are competing factors. You must remember that. Now, this is a contrast. As people have shown how the rainfall centroid shifts with hemispherical temperature. So this is also now getting very popular, and people are able to use that to explain what happened in the Holocene. And so I will leave that part out, this detail. Now I come to the last part. I put it there only because Professor Peter Molnar is here, so I couldn't resist saying a few words about it. And this is about the role of Tibet. The role of Tibet has been talked about the last 60 years, and the major argument was that Tibet is elevated heating which causes circulating changes. Now, it has been built into as a hypothesis. It's based on Lansing contrast theory, but we found that it is not right. And but if you see 10 years back, a lot of people attributed everything that happens to monsoon to Himalayas, and you see a series of papers on that. And Peter Molnar himself wrote a nice paper in 1993 invoking this hypothesis. Okay, but we did a simulation using the NC-MRWF model, the older model, not the present version, and we removed the mountains and found that when you remove the mountain, of course, the onset delays, but after the onset, there is no change in the monsoon. What it says is that once the monsoon has established, it is a king. It takes over. Orography plays no role. This was counterintuitive again, and to show that further, we show the role of Tibet. In one simulation, we removed Tibet, and the other we removed the Western Himalaya. And to our surprise, over central India, when we remove Tibet, nothing happens. That's the red thing. When you remove Western Himalaya, it shifts by about a month, showing that the impact of monsoon is because the Western Himalaya is blocking the moisture from the cold, dry air from the Central Asian region. And this is the hypothesis that was proposed in the thesis of my student Arindam. At that time, I had interaction with Peter Molnar. It was very useful. And so others have now confirmed what you have said, that it is true. And Peter Molnar and Balaji Rajagopalan published papers showing that correlation between heating intermittent plateau and monsoon disappears at the height of the monsoon. That is between July 15th and June 15th and August 15th, and it reappears. So it's a very interesting point that yes, in the onset phase, Tibet is important, but after that, it plays no role. Okay. And this was finally put together nicely with a good wordsmithing by Boos, showing the dominant control of monsoon by orographic insulation, that is preventing temperature and moisture from Central Asia rather than heating. Okay. And this was brought out nicely. He showed that the highest temperature in the upper troposphere is not over Tibet, but over India. So this is a very nice, stunning explanation that Tibet is not the major source, but the highest point is India. Okay. And then Peter Molnar wrote a very nice review a few years ago, and I'm told that he will say more things over the afternoon, so I will not say anything more. So he pointed out how the views about Tibet has changed, and he says it is still changing, so I will leave him to tell us more this afternoon about that. And although the paradigm shift from landscape contrast to energetics is slow, it's happening. There are many new papers appearing in the last few years which give this perspective, and this was a nice review paper which incorporates that, and I hope all the young people here will adopt the new framework, because the old framework is not relevant. So I'll stop here. Thank you. But they used it, I have to accept that precedence, but it is not the stability as we think about in partial theory. This is the argument that if the moisture energy of the upper layer is higher than lower layer, then it requires more effort to transport mass. That's the point here. It is not the partial stability. Please go through the paper carefully on that.
Okay, thank you, Professor Srinivasan. We'll move on to the next presentation by Shange. We will talk on ocean science and fisheries.
Good morning, and it's an honor to follow my mentor from a long time back. JS taught me thermodynamics, which I audited, and a lot more while I did my master's there. So it's an honor to follow him. Thank you for arranging this order. My talk today is two things. One which I have been doing for most of my career, and that's ocean sciences, specifically physical oceanography. And the other thing is what I have been doing with my colleague AC Anil and some others over the last decade or so. So most of what I'm going to tell you has evolved over many cups of tea with Anil and some other colleagues. It's two parts. The first one is connecting the physical forcing and the nature of fisheries. I'll explain what I mean by that. And the other is a proposal for a project that couples ocean sciences and fisheries. It's actually based, the first part is based on one paper, but it subsumes an amazing amount of work that's been done partly by me, but by a lot of people over a long period of time. So the physics is not something I'm going to emphasize. So what I'm going to emphasize is how do you use something that is very rigorous and apply it to something where the reasoning is necessarily heuristic, that is fisheries. The basic observation is not new. If you look at the fisheries, you find that of Gujarat, you find more carnivorous fish like Bombay duck. And if you go down south to Kerala, you find sardines. These are the two dominant fisheries. In between, you get mackerel. The question is why? And the answer, it looks like, lies in the physical forcing. We need to know a little bit about the marine food web, but I'm going to restrict attention to just a few details. You have the primary producers, that's phytoplankton. They're eaten by zooplankton, which are eaten by small fish and then big fish. This is a long food chain in which you have zooplankton, small fish, and big fish. So the Bombay duck would be something like this, and it feeds on smaller fish. You could also have a situation where you have the phytoplankton eaten directly by small fish and then by big fish, or you could have phytoplankton, zooplankton, and intermediate trophic levels in the fishery. It turns out that if you have less food, low nutrients, the environment leads you to a longer food chain. And if you have high nutrients, you often tend to get a shorter food chain. So that is all we need to know about the marine food web. To synthesize food, we need light, which is restricted to roughly the top 100 meters. Oxygen, the concentration is high near the surface where the wind mixes the water, and it decreases below in the oxygen minimum zone. The other thing you need is nutrients, nitrates, phosphates, silicates, and a lot more. Now they are depleted near the surface because they are consumed, and the concentration is higher below. So what the physics needs to do is pump the nutrients into the surface layer where you have light and oxygen to trigger production. So this is how the physics comes into play. There are two ways of getting the nutrients into the upper layer. One is you have a vertical velocity that pushes the nutrients up. That is called upwelling. The reverse phenomenon where you have a downward vertical velocity is called downwelling. Now that's not going to be conducive to triggering phytoplankton growth. So upwelling is a major case where you have isotherms coming up and you bring in nutrients directly by moving them up. The other way is by stirring. You have low nutrients above, high nutrients below. So if by some means you can mix the water above with the water below, then you can enter nutrients into the surface mix layer. Now you can do that by blowing wind, which can also cause evaporation. So the water above becomes denser and it sinks, mixing with the lighter nutrient-rich water up below. So there are two ways in which you can do it, mixing and upwelling. And this is all that we need as far as the physics is concerned. So the entire circulation plays out in order to determine where it will mix, where it will upwell, and thereby enable growth of phytoplankton. There's one more thing that happens. We have a monsoonal climate and a seasonal reversal of currents. Very different from what happens in very well-studied regions like California, where the currents are more or less steady. So this is a picture of satellite chlorophyll from the Eastern Arabian Sea. This is time from April to March, and this is distance northward from Kanyakumari. So this would be Kerala, and this would be Gujarat. Off Kerala, you see one peak that's in the Southeastern Arabian Sea during the summer monsoon. So there is one peak in chlorophyll. There are two peaks in the Northeastern Arabian Sea, one during the summer monsoon and another one during the winter. But you look at this peak of Kerala, it is much higher than what you see over here. Now these peaks are driven by the physics. There are two things that are of interest to us. One is the vertical velocity field. So the circulation has to by some means decide when upwelling occurs, and the other is mixing. The winds must be strong enough, and the circulation must not do anything to preclude mixing of nutrients into the surface mix layer. So if you want to look at upwelling, this is the black curve is for Gujarat, red for Goa, and green for Kerala. Let's not worry about what the data sources are. What you see here is sea level. So when sea level decreases, you have the thermocline coming up and you have upwelling. So sea level decreases during the summer monsoon throughout the Eastern Arabian Sea. So you have upwelling. But the upwelling is stronger in the south, and that leads you to higher phytoplankton. In the winter, the seasonality leads to downwelling. So the conditions are not conducive for pushing nutrients into the surface mix layer. But in the north of Gujarat, you have convective mixing driven by the winds, which are dry. So water evaporates, the salinity increases, the density increases, and you have fairly deep mixing. So if you look at the mix layer, it deepens quite a bit in the north of Gujarat. So what happens in the north of Gujarat is that you have two growing seasons, one during the summer monsoon and one during the winter monsoon. So over the year, most of the months, roughly 10 months, are conducive for phytoplankton growth. While in the south, you have a shorter growing season. So in the north, you have conditions that are conducive to give you a long food chain, while in the south, you have a shorter food chain. But with one difference. In the south, the upwelling is much stronger of Kerala, and that leads you to more pumping of nutrients into the surface mix layer, and therefore you have larger phytoplankton, which are called diatoms, growing off Kerala. So fish can feed directly on these phytoplankton. In the north, in contrast, upwelling is weaker, and therefore you get smaller phytoplankton. There's one more element in the story. Now this map shows you a network of acoustic Doppler current profiler moorings which are deployed in the seas of India. Now these were deployed, they are almost a decade old now in some of the locations. They are deployed basically to measure currents. So this is a major shift in the way we measure the circulation in the seas around India. Earlier we relied only on ship cruises or on climatological data and maybe some inferences drawn from the altimeter. But today we have direct current measurements at several locations along the Indian coast. What the ADCP does is send out acoustic pulses which are reflected back from zooplankton. The assumption is that the zooplankton move at the speed of the horizontal current, and therefore you can look at the reflected signal and construct what is the horizontal current. So you get a profile of the horizontal current above the mooring, above the ADCP. Now there's one more thing that you can do with the ADCP. Though we had deployed it for measuring currents, that the ADCP uses zooplankton to arrive at a measure of the currents implies that you can use the ADCP data to estimate zooplankton biomass. The calibration is not very good yet. We have very meager calibration. It's going to be built over maybe the next decade. But even with the meager calibration available, one thing is striking. You look here, this is chlorophyll in the southeastern Arabian Sea of Kerala. You have this peak during the summer monsoon. But that is also the time when you have upwelling taking place.